This is Math 251 and we're in section 6.7 and we're going to work on to section B here. The second physical concept that we're going to look at as an application of the integral is called work, and the work concept in physics is very specific. The concept of work says that work is done when a force moves an object through a distance. So you have to have a force and it has to move through a distance to be work. For example, if you carry a basket of laundry up the stairs, if you push a stalled car, you're applying a force and it results in something moving, the displacement of an object, and that means work is done. If we have a constant force F, moving our object some distance d in the same direction as the force, and that's really important, then the work done is simply the force multiplied by the distance. Pretty simple equation, W equals F times d. So again, if the object is moved a distance d in the direction of an applied constant force, then work is force times distance. Okay. For example, if we have some object sitting here on the floor, we apply a force, push it, and we move that object over to a new location. Notice that my distance here is the same horizontal direction as the force that was applied. We now have work equals force times distance. Okay. All right, a little bit of background for us down here. A force can be thought of as a push or a pull. That's our most common way of thinking of it. A force basically changes the state of rest or state of motion of a body. There are actually a lot of different types of forces, and if you've taken physics, or if you will, you're going to study different types of forces: centrifugal force, magnetic, electromotive, or gravitational, to name just a few. Since this is a math course and not a physics course, we're going to concentrate on just one. We're going to concentrate on just the gravitational forces for the work that we'll do, but all of the concepts and the math that we talk about extends to the other types as well, and you'll undoubtedly have the opportunity to use that if you do take calculus-based physics down the line. All right, for gravitational forces on Earth, it's common to use units of measure corresponding to the weight of our object. And because we live in the United States, we actually have 3 different units sets that you're probably going to need to be aware of that you may come across. The U.S., of course, is special. We still use our own old system of feet and things like that. Most of the rest of the world does not. But in addition to that, we still, to fit in with the rest of the world, also use the most common, which are the international units, and then another system called CGS that we'll talk about. In order to effectively work in this unit, we're going to need to know something about the various units used in these systems. So I'd like to just start by going over those with you. In this country, our standard unit of distance is the foot, abbreviated, of course, FT. Our units of mass, which we don't talk about very often, is actually called the slug. And the units of acceleration would be feet per second squared. Note, by the way, that the gravitational acceleration constant, which we usually call g, the acceleration due to gravity on a falling body, is 32 feet per second squared. When we get to the units of force, we're going to use one of the most famous physics equations attributable to Newton. Force is mass times acceleration. So if I were to multiply the mass times the acceleration, my units would be slugs times feet per second squared. It looked like that, which I know looks really, really weird. And because it's such a strange looking unit, we typically define a new unit when we get to force. A slug foot per second squared is actually the definition of a pound. The units of work then, since remember work is force times distance, we'd have feet times pounds, and our units of work are going to be foot-pounds. All right, let's go through that same analysis for the international system. The standard unit of measure in the international system is the meter, and most science classes will use that. Standard units of mass would be the kilogram. And our units of acceleration then are meters per second squared. The gravitational constant, the acceleration due to gravity in this system, would be 9.8 meters per second squared. Okay. All right, force, mass times acceleration. I'll put this up here too. Mass times acceleration would be kilograms times meters per second squared. And just like here, that's getting to be really unwieldy, so we just define this. We give it a new name, and this is called the Newton, abbreviated with a capital N. And so when we do work, force times distance, we get newtons times meters, or Newton meters, is a standard unit of work in the international system. Finally, we have the CGS system. You can kind of think of this as sort of a subsystem for the international system. The meter and the kilogram are convenient if whatever we're measuring isn't too small. Of course, a meter is roughly a yard. Kilograms about 2.2 pounds. So if you're working with very small distances or very small masses, this is not a great system. And then we tend to use CGS instead. Here we're going to use the centimeter, a hundredth of a meter, as our standard unit of distance. The gram as our standard unit of mass. And our units of acceleration in this system would be centimeters per second squared. Again, since a centimeter is a hundredth of a meter, it's probably not surprising that we just multiply by 100 here. And our gravitational acceleration constant is 980 centimeters per second squared. As far as force, force is mass times acceleration. So we'd have gram centimeters per second squared. And just like before, it's unwieldy, so we give it a new name. This is called the dyne. Work equals force times distance. And so let's see, force times distance here would be dyne centimeters. All right, one last thing. Although it's very, very common to leave the units of work as foot-pounds, Newton meters, or dyne centimeters, there is one more renaming that sometimes occurs. You're not required to do this, but I'll just let you know in case you see it in future classes. The Newton meter is also sometimes renamed. It's also a joule. And the dyne centimeter also has another name. It's an erg. By far in science, the international system is the one that you're going to see the most. Although again, in this country, you'll still see the US units somewhat frequently. This is somewhat uncommon, but I want you to know it's out there so that you can use it when needed. All right, in addition to that, I'm going to make us a quick little list down here of useful equations before we start tackling our examples. A couple of them we just talked about, but there's one that's a bit older. Ultimately, our goal is going to be to find work. Force times distance. We've just been mentioning that this little relationship, force equals mass times acceleration, is often useful. Sometimes you'll have to use that to figure out your force to plug in here. And then I want to remind you of an equation that we used in the last video. Mass equals density times length, right? If you've got some kind of a thin bar, or a thin wire, or something like that, remember how we said last time, if you take the density times the length, that gives you the mass. Sometimes you'll need to use that to get mass in order to use mass to get force in order to plug the F in here. So these are kind of cascading equations, if you will. You won't need all of them in every problem, but they're helpful when you do need them. All right, let's go ahead and take a look at some examples. In this first example, we'd like to find the work done if we're going to lift a 50-pound object 4 feet. So I know work is force times distance, and I'm just going to start these problems out by making a list. When we get to more complicated problems, developing this habit is going to be good. In this case, everything we need is actually given. The force was given, it's 50 pounds. The distance was given, it's 4 feet, so we can literally just plug in. By the way, if you're ever not sure that you have what you need, compare the units to the chart. I've listed my force as 50 pounds, and in the US units of force are pounds, so I know I'm okay there. All right, so work then, just 50 pounds times 4 feet, or 200 foot-pounds. No big deal. All right, let's try part B. I want to find the work done in lifting a 10-kilogram bag of cement 3 meters. So again, work equals force times distance. And my force this time is actually not given, right? I was given mass of 10 kilograms. That's a mass unit, not a force unit, right? If we're an international system, kilograms are mass. I need newtons for my force. So I'm going to have to say, well, let's see. Force is actually equal to ma. So I'm using that second of our typical equations that get used. The mass is 10 kilograms. And either I know, or again, I can look it up. In this system, the units of acceleration, my gravitational acceleration is 9.8 meters per second squared. And so multiplying there gives me 98. And instead of writing out that big kilogram meter per second squared, I'm just going to use the fact that that really is the Newton. So there's my force. Distance, they did, thank goodness, give me 3 meters. And now I've got both F and D to plug into my work equation. Giving me 294 Newton meters, or I could write that as 294 joules, means exactly the same thing. All right, part C, I'd like you to change this problem a little bit for me because I want to show you kind of how the cascading equations can really work. Let's determine the work done in lifting a block 8 centimeters. And I'd like you to add this information. Instead of telling you it's 25 grams, instead I'd like to say that the block is 6 centimeters long and has a density of 4 grams per centimeter. So, ultimately I want work equals force times distance. Now to get my force, I'm going to say I wasn't given the force, so I know I can use force equals ma. But in this case, I actually wasn't given the mass either, so I'm going to have to go one more. Mass equals density times length. Now I've got information that I have. The density was 4 grams per centimeter, and the length was 6 centimeters. Notice our centimeters will cancel out here, giving us a mass of 24 grams. Okay. Now I can come back over here and plug in. Let's see, mass we just figured out was 24 grams times acceleration. We're in the CGS units here, so my acceleration due to gravity is going to be 980 centimeters per second squared. And 24 times 980 is 23,520. Again, instead of writing grams centimeters per second squared, I'm just going to notice that that unit was renamed the dyne. All right, finally, I can come back over here. I now know the force, 23,520 dynes, and distance here was 8 centimeters. And if I multiply that, I got 188,160. Either dyne centimeters is acceptable, or that's the one that was renamed the erg. Either answer, perfectly fine. Right. By the way, I didn't happen to throw one in here, but you do want to be really careful to make sure that your units are consistent. Notice that as soon as I knew I was in dynes, I had to be in this unit system. Therefore, my units of distance had to be centimeters in order to be consistent. You want to make sure all your units are consistent. One of those 3 rows, not a mixture between them. So, for example, had my distance here been given in meters instead of centimeters, I would have had to have converted. If this had been 8 meters, for example, I would have had to put it in as 800 centimeters. Make sure your units are all consistent within one of the 3 systems that we've defined. All right. So what made those 3 examples pretty easy? You might have noticed we haven't used much calculus yet. What made this pretty easy was the fact that in each case, the force that was involved was constant. If we use a variable force on our objects, this is where calculus comes in, okay? Because the amount of force is going to change as the object changes its position. Here's an example to get you thinking in the right direction. In that, part B, we were lifting that bag of cement. What if our bag had a hole in it? That would mean as that cement drips out, right, that powdered cement drips out, the force is changing because the weight of the bag will change. There's less cement in it all the time. That's a perfect example of a variable force. And we're going to have to handle those kinds of situations using calculus. All right. So, to work with a variable force, what we'll do is we'll always start by finding an expression that represents a little piece of force at each position. Remember, to get the force or weight, we may have to use F equals ma. We're then going to write an expression that represents the distance that little piece gets moved. And then finally, we can write a general expression for a small piece of work. W equals F times D. Now in general, we'd have to add up all of the little pieces, but we've seen this over and over, right? If you're going to add up all of the little pieces, sum up all the little pieces of work, I'll call them W sub I, and then take the limit as the number of pieces goes to infinity. I goes from 1 to n here. That's just the very definition, once again, of the integral. So we actually end up integrating our work expression from, let's just say A to B, the small pieces of work. All right, let's take a look at some examples. We're going to be looking here at 3 specific applications involving work, but again, there are lots of others. For our purposes, we'll do 3. We're going to start here with lifting objects. This is our first work example. And we'll do actually several of these types. So here's my first example. A 200-kilogram cable is 100 meters long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Well, here's my cable, let's say, and I'm going to define my system so that x equals 0 is ground level. And let's see, the very top then, the cable is 100 meters long, so let's let x be 100 at the top. The problem that I have here is that when I'm lifting this thing, I can't just say, well, I'm lifting the whole 200-kilogram cable 100 meters, because I don't have to lift it all 100 meters, right? I have to lift this part at the bottom 100 meters, but this part in the middle, I only have to lift that part 50 meters, and the part near the top, I maybe only have to lift 1 or 2 meters. So I can't consistently say I'm lifting that entire cable the full 100 meters. So let's follow the advice we have up here. We're going to go ahead and we're going to think about what happens for a small piece. I'm going to say it's some random height x. Let's imagine a little tiny piece of cable here. Okay. I'm going to say that little piece has length delta x. You've seen this lots before, right? Those delta x's, eventually we can shrink them infinitesimally small. And that's a small piece of cable at height x. Since its height here is already x units off the ground, what that means is I only have to lift it the rest of the way. The distance that I have to lift it is actually 100 minus x. So for this small piece, let's create our work equation. We know that work equals force times distance. And I'm not given the force, so I'm going to go to my next level. Force equals mass times acceleration. And the problem is I don't really have the mass for that tiny little piece. I have the mass for the whole cable. But remember, right now I'm only working with a small piece. So I'm going to have to go one more step. Mass equals density times length. For this tiny little piece, I know the length, it's delta x, but what about the density? I'm going to actually have to get the density from this information in the problem. The density of this cable is going to be over 200 kilograms, or the 200 kilograms is spread over 100 meters. So the density is actually 2 kilograms per meter. So for my mass, I'd have 2 kilograms per meter times my length, delta x meters. Meters will cancel out. And my mass is 2 delta x kilograms. We can come back and use that here. Put in our mass. And then, as always, we want the acceleration units. We're in the kilograms and meters, so we're in international. My acceleration due to gravity would be 9.8 meters per second squared. Okay. And if I multiply that, that's going to give me 19.6 delta x. And kilogram meters per second squared is actually newtons. All right, finally I have a force that I can plug in here. Times the distance, and again, this little piece, the distance I have to lift that is 100 minus x. Meters, sorry, lots to squeeze in here. So ultimately, that's my expression for work. All right, let's now translate this to the whole cable. To do the whole cable, we're going to integrate this small pieces of work. So the work for the whole cable is going to be the integral of our work expression, 19.6 times 100 minus x. And of course, like we've seen many, many times, right, the delta x shrinks down infinitesimally small when we write the integral and becomes a dx. Since my little pieces of cable are going to go from a height of x equals 0 to a height of x equals 100, that provides me with my limits of integration. And again, most of these limits aren't really, or excuse me, most of these integrals aren't difficult to do. So just to save us some time, I've pre-done them just using technology. And you can use technology too when you evaluate them. So I'd have 9,800, and notice that's Newton meters when I do that integral. All right, let's do one more very similar to that. In this one, we have a 20-foot rope hanging vertically from a winch. The rope weighs 0.08 pounds per foot. Find the work done in pulling the entire rope up. Let me get this so I can see something up here. There we go. All right. So, same basic diagram. We're going from x equals 0 to, oops, x equals 20, not 100 this time. Right. 20-foot rope. And so once again, I'm going to imagine just at some random height x, some small little piece of rope here. And that little tiny piece we'll say has length delta x. And this is just a small piece of rope at height x. Since it is at height x, that little piece only has to be lifted the rest of the way, which would be 20 minus x. And so I'm now going to go ahead and say for my small piece, let's figure out the work to lift just that one little tiny small piece of rope. So again, we know that work is force times distance. Now, this problem is a little bit different because notice I've given you something here that does look like a density, right? Doesn't that look like a density? But it's a little bit different density than the ones we've been working with until now. The problems that we've done so far have always either been given or we've been able to figure out the mass density, right? Here we had a mass density of 2 kilograms per meter. This is actually a weight density. It's already in pounds. I don't have to convert to get my F equals ma. So while this was a mass density, this time I actually have a weight density. So I'm actually going to introduce a slightly different equation this time. I'm going to say, in order to get my force, if I take that weight density, which I'm going to call delta, and multiply by the length, I'll actually already have pounds. I'll already have the force. I don't need to convert with the F equals ma. So if you want to, down in your useful equations, we could add a new one. we also have F equals, and I'm going to call it delta times L, where here, this is when we have a mass density, and this is where we have a weight density. It just depends on the information that's given that you know which way you're going to go. All right, so because we do have the weight density this time of 0.08 pounds per foot, and we're talking about a little piece of rope of length delta x feet. Feet are going to cancel, and our force is 0.08 pounds. Again, always double checking, right? Pounds is a force unit, so we've done this correctly. All right, so let's see. I think we know everything. We know that our force was 0.08 pound. I'm sorry, I lost the delta x. 0.08 times delta x. 0.08 delta x pounds. Our distance is the 20 minus x feet. And so there's my expression for a small piece of work. I can now do the whole rope. Work for the whole rope would be the integral of this work expression, 0.08 times 20 minus x, times the delta x, which will turn into a dx when we make it infinitesimally small. And we're integrating from pieces of rope at height 0 through pieces of rope at height 20. Again, feel free to use technology here. We're just going to plug that in, and if you integrate that out, you should get 16, and this would be foot-pounds. I'm going to call that W rope, because we're going to use that value again in just a couple of minutes. All right, we're going to continue. This is just part A of this example. We're going to continue and do a bit more with the same situation. Let's now imagine that on this rope, we've attached an empty bucket weighing 5 pounds. I now want to know what's the work done in pulling the rope and the bucket all the way up to the top. Well, let's see. We've already figured out the rope part, right? We've now got this bucket down here, and we know that that bucket weighs 5 pounds. And we want to pull it up the full 20 feet. In this case, there's no variable force. That 5-pound bucket stays 5 pounds the entire time, and the whole thing goes up the whole 20 feet. So I don't need calculus for this one. I can just say right away, work equals force times distance. The force is the constant, 5 pounds, and the distance is the 20 feet. So I'm going to say W for the bucket is going to be 100 foot-pounds. Okay. My goal here, though, was to find the work done in pulling the rope and the bucket all the way up. So the total work is going to be this 100 that we just calculated, plus the 16 that we got in part A, or 116 foot-pounds, to lift the rope and the bucket. All right, one more. Now let's suppose our bucket contains 16 pounds, which is about 2 gallons of water. The bucket is leaking in such a way that this bucket runs out of water just as the bucket reaches the top. How lucky, right? I'd like to find the work done in pulling the rope, the bucket, and the water all the way up. Right? So this is a classic example of a variable force. Although the water weighs 16 pounds at the beginning, by the time we get to the top, the water actually weighs nothing because it's all leaked out. Right? So we're going to have to deal with that variable force. Now we don't have to worry about the rope and the bucket. We already know how much work we're expending to lift those. We only have to worry about the water. So let's think about our water just a little bit here. Got our picture, and I'm going to say that let's imagine my bucket moving through some little distance here, delta x. Notice this is a little different. Delta x this time represents the distance that's being moved. And the reason I have to do that is because the force, the weight of the water, is different at each height because of the leak. So I can only apply a specific force to a very tiny little short piece of distance. This, of course, is going to be shrunk infinitesimally small, so we'll eventually say we can figure the weight of the water at each specific height, moving the distance that it needs to move. All right, next, I'm going to go ahead and here, we've got it right over here, but I'm going to add it over here. This is my x equals 0, where the bucket starts, and this is my x equals 20, where it stops. And let's go ahead and assume that this is some random height x, where this little piece of distance that I'm moving through is located. I need to figure out the force. I need to figure out how much of water, or what weight of water, is in the bucket at that particular height. There's lots of ways to do this. For me, the simplest way is just to figure out the little linear equation that I would get. I'm going to say at height x, what is the force or weight of water? And since I actually know 2 points, it's going to be pretty easy to make that into an equation. I know at height 0, at the beginning, we had 16 pounds of water. I also know that at the end, at height 20, all of the water is gone, so I now have 0 pounds of water. And let's see, the heights are in feet. The weight of the water is in pounds. And if I just make that into a simple little linear equation, my slope would be negative 16 over 20, or negative 0.8. The y-intercept is 16, so I'd have the y or f value is negative 0.8x plus 16. And that would be in pounds of water. So, delta x is my distance moved in feet. F is negative 0.8x plus 16. I've got everything I need. My little piece of work, moving it just through that small distance, is force times distance, negative 0.8x plus 16 times delta x. And I missed my units. That would be pounds, and that would be feet. So I do have foot-pounds, a legitimate set of units for work. All right, we got the small piece. We are ready to do the whole thing. I'm going to integrate my little piece of work here. Negative 0.8x plus 16. The delta x becomes infinitesimally small, the dx. And we are going all the way from 0 to 20 again. Once again, simple integral. It's not that you can't do it by hand, but just for speed, I went ahead and did this one on the calculator, and I got 160 foot-pounds. Okay. So ultimately, to lift the rope, the bucket itself, and the water that's steadily leaking out, the total work that we would have for this entire system we're going to add up all the pieces, 16 pounds for the rope, or foot-pounds for the rope, plus the 100 foot-pounds for the bucket, plus the 160 foot-pounds for the water. giving us a grand total of 276 foot-pounds of work to do this job. All right, that is the first work application we're doing, the lifting problems. We'll come back in the next video and take a look at a couple of other work examples.